Section 7.4, Nuclear Fission. In this section, we're going to talk about nuclear energy produced using the principle of nuclear fission. We're going to solve problems calculating energy that is released during the nuclear fission reaction. Also, we're going to talk about some environmental and safety concern in application of the nuclear fission producing electricity. Let's start with a mass-energy equivalence. The famous energy mass formula proposed by Einstein is energy is equal to mc squared when m is mass, c is the speed of light, which is 2.99 times 10 in power of 8, or if you round it, it's a 3 times 10 in power of 8 meter per second. Remember that we talk about conservation of the mass, basically grade 9, grade 10, and conservation of energy in grade 11. However, the notion of the conservation of the mass and conservation of the energy now is replaced by a more general law of conservation of mass energy. Law conservation of the mass energy says mass can be transformed into energy and the energy into mass such that the total mass energy in an isolated system remain constant. An isolated system is a system where no energy flows into or out of the system and no mass is added or removed from the system. Mass and energy are different aspects of the same phenomenon. However, the mass-energy equivalence theory gives life to the nuclear power generation. Nuclear power reactors emit almost no pollutant into atmosphere, but they produce harmful radioactive waste that must be safely contained and stored for a long period of time. Nuclear energy takes a fair portion of the energy production everywhere in the developing world. Here are some data. In Ontario, for example, 61% of the energy produced is done through nuclear reaction. In Canada, almost 15% of the energy it is a nuclear energy. In the United States, almost 20%, and on the world is 4%. It's more to come. We are familiar now with the atomic mass unit, which is commonly used in chemistry and physics as a more convenient unit of mass than the kilogram because it is a very small unit. One atomic mass unit is equivalent to the mass of 1/12 of the carbon-12 atom, or atomic mass unit is equal to 1.66 times 10 in power of negative 27 kilogram. So here you have a table of data. It's very important in this chapter. So mass of the proton is equal to 1.672614 times 10 in power of negative 27. So mass of a proton by using atomic mass unit is 1.007276. Neutron is 1.674920 times 10 in power of negative 27 kilogram, and in an atomic mass unit is 1.008665. For electron is very small, 9.10956 times 10 in power of negative 31 kilogram, and in an atomic mass unit 0.000549. So those values in this table, we're going to use it to calculate what we call a mass defect. The mass defect is a difference between the calculated mass of the atom based on nucleons, so protons and neutrons, and electrons present, and the actual atomic mass that we get it from periodic table. Mass defect is calculated by total mass minus mass that is already given through a periodic table. So total mass that is calculated based on all particles, subparticles of the atom, protons, neutrons, and electrons, minus the mass that is already given to you based on an atomic mass. How can we explain the difference between the total mass of the all subatomic particles and the mass of the atom itself? This difference, this missing mass, exists in form of energy, which is used to hold nucleus together. This energy is called binding energy. The binding energy is the amount of energy that would be needed to separate all the nucleons, which are protons and neutrons, in a nucleus. The formula is, as a Einstein mass energy equivalence, is energy is equal to change in mass or mass defect times c square. When calculating the binding energy, make sure to use kilogram as a standard unit, so the energy is in joule. So you can convert atomic mass unit into kilogram. In order to convert atomic mass unit into kilogram, you can use that conversion rate of 1 atomic mass unit is equal to 1.66 times 10 to the power of negative 27 kilogram. Now, for binding energy, that energy is very small, and joule is very big unit to calculate that energy. So that's why we use a much smaller unit of energy that is used in nuclear physics. This unit is mega electron volt. 1 mega electron volt is equal to 1.602 times 10 to the power of negative 13 joule. Let's do a practice with a mass defect and binding energy. Determine the mass defect and binding energy of the lithium-7 nucleus, given that its actual atomic mass is 7.01600 U. Let's start with the calculate the total mass of these subatomic particles. Lithium-7 is third in periodic table, so there's 3 protons. Atomic number is 3, so 3 protons, 3 electrons. Since that is lithium-7, that means 7 minus 3 is 4, so 4 is equal to a number of neutrons. So that's why we just add them together, 3 protons plus 4 neutrons plus 3 electrons. Using the table on the top right corner, when you have atomic mass unit for proton, neutron, and electron, we can actually replace masses with what masses are equal to. Then we get the total mass is equal to 7.058135 U. Please do not round. Please keep 6 to 7 significant figures, because that difference is very small, so we don't want to round it. That mass defect is total mass minus mass that is given. So total mass we just calculated is 7.058135 U minus the mass that is given, 7.01600 U. And then we got 0.042135 U. But in order to calculate binding energy, we need to convert it into a kilogram. So then mass that we just found, 0.042135 U, we multiply it by 1.66 times 10 to the power of negative 27 kilogram per atomic mass unit. Those U cancels, atomic mass unit cancel, and we got the mass defect in kilogram. 6.9944 times 10 to the power of negative 29 kilogram. Then we are ready to calculate the binding energy using that mc square formula, but this time with a change in mass or mass defect. That is called binding energy. So binding energy is equal to mass defect times c square. We already calculated 6.9944 times 10 to the power of negative 29 times 3 times 10 to the power of 8 meter per second, and all in the power of 2. Make sure that all in the power of 2, because 3 is has to be in the power of 2. 10 in the power of 8 has to be in the power of 2. Meter has to be in the power of 2. Second has to be in the power of 2 in order for that to calculate. So after doing the calculation, you get 6.2950 times 10 in the power of minus or negative 12 joule. I encourage you always when we do a calculation, get your calculator and try it yourself. Always, because that's how you practice. Or sometimes pause the video and do it yourself. Do it yourself. Okay, and now we can convert this one energy to what is more appropriate energy unit for that small energy that is produced by one atom. So when we're talking about nuclear energy, we're talking about energy of the one nucleus, which is very small. However, we have trillions and trillions and trillions of the atoms actually that undergoes that nuclear reaction. So that's why we produce enormous amount of energy. However, that's what we start with at the energy at the nucleus level. Okay, if you want to convert it, because if you see that energy is at the power of negative 12 joule, it's very small number for joule. We convert it by dividing by 1.602 times 10 in the power of negative 13 joule per mega electrovolt. Then the answer would be 39 mega electron volt. So that energy that comes from just that binding energy from just one nucleus only. The reason that we study nuclear fission is to harvest that nuclear energy, to use it. So nuclear fuel is a radioactive material that is used to power a nuclear reactor. When a nuclear fission occurs, the binding energy of the nucleus is released and it is converted into a useful type of energy like electricity, electric energy. Some radioactive isotopes with very large mass numbers undergoes a nuclear fission when they struck by a neutron. The amount of energy produced in a nuclear fission reaction is about 7 million times as great as the energy released when the same mass of the dynamites explode. That's why we have enormous amount of energy for very small mass. You're going to see later on the amount of mass that we use on a nuclear reaction, the pellet, is very small. It's 1 to 2 centimeter small. A radioactive isotope used as a nuclear fuel in a nuclear fission reaction is uranium. For example, uranium-235 can be split into a krypton-92 and a barium-141. The equation for this nuclear reaction is uranium with 1 neutron will give you krypton plus barium plus 3 free neutrons plus binding energy. I want to draw your attention toward conservation of the mass and conservation of the charge. Take a look. If you see the mass is 235 and plus 1 is 236, that is equal to 92 plus 141 plus 3. Conservation of charges. 92 is equal to 36 plus 56. So that is something that you have to look at when you write a nuclear reaction equation. Some other examples of fissionable isotopes are thorium-232, uranium-233, and plutonium-239. So if enough fuel is present, a series of reactions can occur. Some of those 3 neutrons, or all 3 of them, produced in a previous reaction, can be used to generate further reaction. How does it happen? So let's say that this is one of those 3. if there's a more fuel present, so more nucleus of uranium-235 is present, then this neutron is going to hit uranium-235, becomes uranium-236, and in the same way as before, is going to disintegrate into two elements that we already saw. The series of elements can be barium and krypton, or antimony and niobium, rubidium or cesium, or strontium or xenon. So any of those combination plus 3 extra neutrons, and that will continue. So those neutrons produced in this one is going to hit another nucleus of uranium-235, and this is going to continue. Series of nuclear reaction will continue. So a chain reaction is a repeated series of reaction in which the product of one reaction generate subsequent reactions. Chain reaction occurs without requiring any material added to a system. The amount of nuclear fuel required to cause a chain reaction is called critical mass. So critical mass is a minimum mass of the nuclear fuel required to cause chain reaction. Chain reaction induced by fission of uranium-235 produce unpredictably this pair of elements during the nuclear reaction: barium and krypton, antimony and niobium, strontium and xenon, rubidium and cesium. And this is how the chain reaction will look like. It starts with one neutron hitting the nucleus of uranium-235 and becomes 236, unstable isotope, and is going to disintegrate into barium and krypton and releasing 3 more free neutrons. Then those 3 free neutrons, if they slow down, so absorb a lot of, and we absorb a lot of energy from that environment using a heavy water. We're going to talk about that later on. And those 3 free neutrons will become ready to hit next uranium nucleus, and that chain reaction will continue. And sometime you have barium and krypton, sometime you have antimony and niobium, sometime you have rubidium and cesium and strontium and xenon. So that's pretty much how it goes until it will end up with a series of alpha and beta decays. We're going to end up at the bottom of the chain reaction, which usually end up with lead. So that is radioactive lead, and that will be a nuclear waste. The neutrons that are released during the chain reaction are too high in energy to be absorbed. So they need to cool off, slow down, using a moderator. And moderator is a heavy water. Heavy water, which is 11% heavier than a normal water because of the deuterium or hydrogen 2, is used as a moderator to slow down neutrons and prevent neutron leakage. After moderation, neutrons' kinetic energy is about the same as other materials surrounding them. So once the high energy neutrons has been moderated, then it can be absorbed by another uranium-235 nucleus, and that chain reaction will continue. Here's a practice problem. Calculate the energy released in a fission reaction by calculating the mass defect between the reactant and a product with the masses given below. So everything is given. Mass of uranium-235 is 235.044. Mass of cesium-140 is 139.909 U. And mass of rubidium-93 is already given, 92.922. And mass of neutron is 1.009. Mass defect and binding energy is required. Here is a reaction. Uranium-235 with 1 neutron will give you cesium-140, rubidium-93, and 3 extra neutron. Because if you see there's a neutron and neutron on both sides, so we have 1 here and we have 3 here. So if you cancel that 1, well, this will become 2. So that's why we have more simplified version of that nuclear reaction. Then you can calculate mass defect using those values on the top. So uranium-235 minus whatever product is there is like a cesium, rubidium, and 2 neutron. Then you can plug those numbers and we get binding mass defect is 0.1950 atomic mass unit, but we need that to convert it into kilogram in order to get in joule. So we can multiply by 1.66 times 10 to the power of negative 27 kilogram per unit, atomic mass unit, and the U and U cancel. So what we have is 3.237 times 10 to the power of negative 28 kilogram. Now we can calculate binding energy in a joule and in a mega electron volt using that famous formula mc square. So change in mass or mass defect, which already is calculated in a kilogram, times c square, which is 3 times 10 to the power of 8 meter per second, and all in the power of 2. I want to draw your attention here because many people make that mistake. They forget to square both, put that in the power of 2 for both. 3 square is 9, and 10 in the power of 8 in the square of 2 in the power of 2 will make 10 in the power of 16 meter square divided by second square. And then you get in joule. And if you do that in your calculator, you'll get 2.91 times 10 to the power of negative 11 joule. Now last step will be converted into a mega electrovolt, because this energy, as you see, is very small in atomic level. So in order to make sense and be easier, you can convert it to a smaller unit, which is 1.602 times 10 to the power of negative 11 times smaller. So that's why you divide that by 1.602 times 10 to the power of negative 11, which is joule per mega electrovolt. And you're going to joule and joule cancel, and you're going to get energy is equal, binding energy is equal 181.6 mega electrovolt. Here is another practice problem similar to a previous one. Calculate the energy released in a fission reaction by calculating the mass defect between reactant and products with the masses given below. We have uranium-235 with a mass 235,044. We have xenon 134.879. We have strontium 89.908, and we have a neutron 1.009. Okay, so the reaction equation would be uranium-235 with 1 neutron will give you xenon 135, strontium 90, and 11 neutron. So we get rid of 1 neutron on the left and 1 on the right, and we end up with 10 on the right. And then we can do calculation using those masses above. So we have all masses here. Then mass defect is difference between a reactant, which is uranium-235, minus products. So we have xenon, strontium, and 10 neutrons. As I said, you can replace masses here with what was given, and we have 235.044 minus, open bracket, 134.879, 89.908, and 10 neutrons, that's 10 times 1.009. If you do that calculation, you will get 0.1670 atomic mass unit. Now we can convert that in kilogram to get that energy in joule. So by multiplying it with a 1.66 times 10 to the power of negative 27 kilogram per atomic mass unit. And we get 2.7722 times 10 to the power of negative 28 kilogram. Now we're ready to calculate binding energy in joule and in a mega electrovolt if you need to do it. So in joule, you can use mass in kilogram, and that C square, remember that you have to square everything. 3, 10 in power of 8 has to be in square, and meter per second has to be squared as well. So after you do that calculation, you're going to have 2.495 times 10 to the power of negative 11 joule. Now we can convert it to a mega electrovolt by dividing by 1.602 times 10 to the power of negative 13, and then energy is 155.7 mega electrovolt. So you can do similar at any problems that you need to do. Some of the nuclear reactors use only natural uranium as fuel. Natural uranium consists of 99.27% of uranium-238 and only 0.72 uranium-235, which is a radioactive isotope. Now, fuel bundles consist in uranium rods. So this is fuel bundles look like, and those are uranium rods, are long, that's 4 meter long approximately. And inside of those rods, you have several hundreds of natural uranium pellets. Those pellets are very small. You see that 1 to 2 centimeter. And that's how you can keep that nuclear power plant running without refueling it, because everything is already ready there to supply those pellets one after the other, etc. These fuel bundles are responsible for driving the chain reaction within a reactor core. Let's take a look of the reactor parts and the process. Calandria is a core of the reactor, consisting of fuel bundles, control rods, and moderator. Fuel bundles are fuel elements consisting of uranium pellets. We talk about those. Control rods are adjustable cadmium rods used to control nuclear reaction rate. They can even shut down the nuclear reactor. We're going to talk about this in terms of security. Moderator is a heavy water used to slow neutrons and absorb thermal energy to be used for generating steam and speeding a turbine and generating electricity. Primary loop is a closed loop through which heavy water flows. So they have two functions. They act as a moderator to slow down those neutrons to be reused in a chain reaction, and to get that thermal energy to loop through that generator, steam generator. So steam generator absorbs the thermal energy from heavy water in a primary loop and producing steam. And that steam travels through secondary loop, which is closed loop through which a normal water, which becomes steam, flows. So that normal water gets the heat from the primary loop, will generate the steam, and that steam is going to travel toward turbines, and turbine is going to be spinning, and turbine are connected with a generator, so that energy will be produced. As neutrons and thermal energy are produced, heavy water both moderate neutrons and absorb thermal energy. We'll mention that before. As a heavy water flows through a primary loop, thermal energy is transferred to a steam generator again, and cycle repeated. So that's how that energy is absorbed from calandria, and at the same time help the chain reaction to happen. And again, steam generator uses the absorbed thermal energy to heat the normal water in the secondary loop to produce steam. And steam is sent to the steam turbine, where it's a high pressure, causes the turbine to turn, and an electrical energy generator is connected, and then is used to convert the mechanical energy of the spinning turbine into electrical energy that is being. So there are some safety considerations regarding to how to protect the nuclear reactor from overheating, overrunning, and another thing is how to slow down that nuclear reaction, or even to shut it down for repair, for example, or in terms of something uncontrolled, like a natural disaster or any other thing. So how can we control a nuclear reaction in a calandria, or how can we stop it? Rods are inserted into a core vertically from above and suspended by electrically controlled magnet. If something happened, any disruption of electrical power to the reactor, the magnet automatically turned off because they are electromagnet, causing the rod to drop completely into a core, slowing down and shutting down that reactor. So this immediately stopped the chain reaction, ensuring the safe reactor shutdown. How that can happen? Those cadmium rods or control rods will absorb those free neutrons. If you remember from the chain reaction, you need those free neutrons. We slow them down in order to be as a source of new reaction. So if we absorb every free neutrons, nothing is going to happen. So that's why you shut down the reactor. When we talk about advantages of nuclear reactors, we said that they emit a very small quantity of pollutant into atmosphere. Okay, but they come with a big price, with a big problem: radioactive waste. Radioactive waste consists in a radioactive byproduct of nuclear power generation that are generally not useful for any other purpose. So these materials must be stored in appropriately sealed containers, in some cases for hundreds of years, until that radiation can diminish. The best method is to store this waste in a safe geological depositories, which are basically abandoned mines, after there is no reason, economically feasibility to keep those mines running, working. You can use those for storage, and that is the best way to store underground, deep underground, those harmful radioactive waste. And this is it for section 7.4. This is section 7.5, nuclear fusion. In this section, we're going to talk about another type of nuclear reaction, which is fusing elements together, fusing nucleus together to form another element. Nuclear fusion is a nuclear reaction in which a nuclei of the two atoms fuse together to form a new element, which is heavier. This type of nuclear reaction powers the stars. For nuclear fission to occur, the fusing nuclei must have enough kinetic energy to overcome the repulsive electrostatic force between them. The nuclear fusion is the cleanest type of energy and more efficient type of energy ever but it is not easy task to achieve in a laboratory, much less to a power reactor in an industrial use. Let's take a look at nuclear stability. Under what condition the nuclear fusion and fission occurs? To understand this, we need to consider relative stability of heavy and light isotopes. The higher the binding energy, the more stable the nucleus. So take a look at the graph. If you see on a smaller masses, we have a sharp increase of the energy, binding energy, until you reach a certain point when it is flat, stable. Then you see that it is noticeable that the binding energy graph rises sharply until it reaches the maximum at atomic mass of 56, which is iron, before gradually decreasing. So after that, still the nuclear reaction is feasible, which this case, the nuclear reaction is fission nuclear reaction, is splitting, because on a heavy elements, it breaks to a lighter elements. You see that energy is increasing. So it releases the energy. On this case is even more noticeable because from a lighter you go to a heavier element, so it is a sharp increase of the energy released. So by comparing those two graphs, we can say that fusion, melting together of elements to become a heavier one, it is feasible for a smaller masses, smaller or lighter nuclei. For fission, splitting from heavy to a lighter, it is on bigger masses. So still energy is released. So for iron, you see that nothing you can do with iron. So this suggests that iron 56 is the most stable of all nuclei with the most tightly bonded nucleus. So nothing will happen with iron 56. Just by looking at the graph, you'll see that nuclear fission, it is most likely to occur with a heavy, very heavy nuclei. So when they break apart, then they produce a lighter elements, and there's a change in the energy because the slope goes decreasing. And there's a change in energy when a heavy nuclei break apart into a lighter one. Now, if you take a look on another side of the graph, it is lighter, very light, a nuclei like hydrogen and helium. If you see there's a sharp increase of the binding energy, that means that when a lighter element are merged to produce a heavier element, that means the enormous amount of energy is released. So in both situations, the total binding energy increase. Both reactions are highly exothermic. So energy is released. This implies that the mass defect has increased. Now you can compare both. So by calculating the energy released in each type of the reaction, you can accurately compare the relative energy output of the nuclear fusion reaction with that of the nuclear fission reaction. And you see very clearly that nuclear fusion is more energy rich. However, it's difficult to produce in lab, let alone in an industrial scale in a nuclear power plant. So the only option for us is nuclear fission power plants. Now let's calculate the energy equivalent of one atomic unit of mass, which is U, measured in mega electrovolt. So we know that mass energy formula is energy is equal to mc squared. But at this time, as we said, we're talking about one atomic unit of mass, which is U. So instead of mass here, we can just put U. And then we know that one atomic mass unit is 1.66 times 10 in power of negative 27 kilogram. And C square is 3 times 10 in power of 8, all in power of 2. And then we can convert it in mega electrovolt by dividing with 1.602 times 10 in power of negative 13 joule. And if you do those calculations, you get a magic number, 933 mega electrovolt. So the energy equivalence of the mass is 933 mega electrovolt. So that's a mass energy equivalence in numbers now. If the equivalence, energy equivalence with one atomic unit of mass is 933 mega electrovolt, then what is equivalence of C square? We can do that too. So again, energy is equal to mc squared, and mass, we're talking about 1 unit, which is 1 U, C squared. That is equal of 933 mega electrovolt. We just calculated it. So that equivalence for 1 unit is 933 mega electrovolt. So from this portion, we can solve for C squared. And C squared is equal to 933 mega electrovolt divided by 1 U. And that's it. C squared is equal to 933 mega electrovolt per 1 unit of mass. So we can use this number instead of converting the unit of mass into kilogram, which take longer, or calculating a C squared every time we solve problems. We can just use 933 mega electrovolt per 1 atomic mass unit. Here's a practice problem. Determine the energy released when a deuterium atom, or D, fuses with a tritium atom, we just label as a T, to form a helium according to nuclear reaction equation below. So we have one hydrogen 2 and one hydrogen 3. Together they merge, fuse together, and create the helium and release 1 neutron. So we can use given masses, mass of a deuterium, which is 2.01410 unit. Mass of tritium is 3.01605 unit. And mass of helium is 4.00260 unit. And mass of neutron, we sometimes use it as 1.009, and this time we can use it more accurately as a 1.00867 unit. We just calculated that C squared is equal to 933 mega electrovolt per unit. So what we need is a mass defect and binding energy. So mass defect, we can calculate the difference between masses of reactant minus mass of product. So two reactant are heavy, two hydrogen 2 and hydrogen 3, deuterium and tritium, minus helium and neutron. So if you use those numbers there that are already given, everything is already given, then you can have 2.01410 plus 3.01605 minus, open bracket, 4.00260 plus 1.00867 and close bracket, and you can plug that in the calculator. You'll get 0.01888 U. So we are now ready to calculate binding energy. The binding energy is a mass defect times C squared. We know already C squared is 933 mega electrovolt per unit, and we have 0.01888 unit. You can multiply this, and you can get as a binding energy is equal to 17.6 mega electrovolt. I already mentioned many times that nuclear fusion in laboratory is very difficult, let alone the nuclear fusion in industrial scale. The conditions that allow nuclear fusion to occur in stars are high pressure, high temperature, and high density of nuclei. So they are closer together, very close together. It's not the density of nuclei, they are heavier nuclei. I mean, they are closer together, compressed. That's why it's high pressure. High temperature, high pressure, they are close together in a very small space. That's why it's a high density of nuclei. Fusion occurs in the stars at the size of Sun and smaller through a process called proton-proton change. Proton means that only nucleus of hydrogen. Hydrogen 1 has only one proton in a nucleus. And we have 4 hydrogen 1 that they are fused together, creating helium and 2 positron and releasing enormous amount of energy. Now, for some other stars that are significantly larger and hotter than Sun, we have a different type of nuclear reaction, fusion nuclear reaction, which is a carbon-nitrogen-oxygen cycle, activating the fusion of the hydrogen and into helium. So this process, as I said, occurs in stars that are significantly larger and hotter than Sun. So as a carbon-12, it is turning into a nitrogen-13, and then in a carbon-13, and then in nitrogen-14, and in oxygen-15, nitrogen-15, and then it will break into carbon-12 and helium. When we talk about nuclear fusion that happen in the stars that are at the size of Sun or smaller, it is a proton-proton. What does it mean? It means that electrons are removed. So proton is already ionized. Proton, it is already just a nucleus of the hydrogen that are fused together to create helium. In principle of the magnetic confinement that is done experimentally in lab, deuterium and tritium are placed in a core of the reactor and heated to extremely high temperature, and that is comparable to the Sun core. So what happened? All materials in that enormous amount of temperature are changed in a fourth state of matter in which all atoms are ionized. So electrons are removed. This is called plasma. And plasma is a requirement condition for a nucleus fusion to occur. However, we are far from doing something very significant with nuclear fusion, and let alone we are absolutely far from doing something that is feasible to produce energy using nuclear fusion on Earth. So that's about it on nuclear fusion. Have a good day.